Imagine a major city instantly plunged into darkness. Elevators halt between floors, traffic lights die, and the hum of modern life stops dead. When the lights go out, we usually look up. We blame lightning strikes, snapped tree branches, or heavy ice, bringing down the physical lines. But the most consistent threat to the global electrical grid hides at a microscopic level, deep within the infrastructure itself. High-voltage equipment relies entirely on internal insulation to contain massive amounts of electrical power. Over time, this material breaks down invisibly. For decades, engineers relied on basic DC stress tests, like Megger testing, to check this insulation. These resistance checks find the dead shorts and the big holes, but they miss the subtle, progressive decay that happens under actual AC operating conditions. Because these basic tests miss the specific wear and tear caused by alternating current, an underground cable can pass an inspection on Monday and trigger a catastrophic blackout on Tuesday. In a flawless system, healthy insulation acts as a perfect capacitor. When alternating current flows, capacitive current leads applied voltage by exactly 90 degrees. In this mathematically perfect state, the material stores and returns all energy, with zero energy lost as heat. Real-world materials face moisture ingress and thermal stress. Inside solid polymer cables, microscopic amounts of water form branching conductive paths known as water treeing. This circuit diagram models the resulting shift. These microscopic moisture trees create a parallel path, introducing a resistive current, labeled here as RV, that leaks directly through the material. This resistive leakage generates heat. That heat further degrades the surrounding insulation, which allows even more resistive current to leak through. Microscopic exponential thermal runaway turns a stable insulator into a conductive path, making catastrophic failure a mathematical certainty. To detect this invisible thermal runaway, engineers use specialized equipment like the tan delta, or dissipation factor test system, shown here. By applying an AC voltage, the test measures the exact phase shift deviation from the ideal 90-degree angle. This geometric deviation is called the loss angle, or tan delta. It gives engineers a precise ratio of the resistive leakage current to the healthy capacitive current. Field measurements present a logistical hurdle. Testing miles of massive underground cable at the standard grid frequency of 60 Hz requires a staggering amount of reactive power from the portable equipment. Testing at a very low frequency of 0.1 Hz solves this problem. It drastically reduces the power requirement while maintaining high sensitivity to the defects found in the resistive current vector. A VLF tan delta test acts as a full-body scan for a power asset, detecting generalized aging across the entire volume of a cable long before localized weak spots trigger a blowout. While a single tan delta measurement provides a snapshot of insulation health, engineers gain deeper insights by trending the data across different voltages. Healthy insulation maintains a flat baseline curve, regardless of applied voltage. Degraded insulation reveals a sharply rising tip-up curve. As voltage increases, resistive current multiplies, indicating water treeing. Tracking this over years lets engineers predict remaining life before the cable crosses a failure threshold. This data enables a shift toward condition-based maintenance. Instead of replacing expensive assets based on arbitrary age limits, grid operators can now prioritize repairs based on actual insulation quality. Proactively tracking these metrics allows utilities to safely keep 30-year-old cables in service while pinpointing and replacing faulty 5-year-old ones, increasing asset utilization efficiency by up to 15%. Modern grid reliability depends on reading the invisible geometry of electrical waves,